right, last question for the week. Probably the last question I'm going to hand you before exam week next week. So here we go. There's 2011 number 6. It says you've got a rigid flask that's 2 liters in volume. There's nothing in it. They take all the air out. They add some ethanol to it. Hold the temperature constant. I see volume and temperature, and there's a pressure somewhere here, and I start to go, I may have ideal gas law in here somewhere. We don't on this one, but there's nothing wrong with that thought. It says the amount of liquid ethanol decreases, but after 5 minutes the liquid ethanol in the flask remains constant. Ethanol has a boiling point of this, has an equilibrium vapor pressure, that's the important part, of 100 at 35 degrees Celsius. So when the amount of liquid ethanol in the flask is constant, is the pressure in the flask greater than, less than, or equal to 100 torr? If the liquid amount is not changing anymore, then it has already vaporized as much as it was going to vaporize at that particular temperature. And so at that temperature, 100 torr, that is the equilibrium vapor pressure, and so the pressure in the flask will be equal to 100 torr because if the quantity of liquid ethanol is constant, we've established equilibrium between the liquid and gaseous ethanol. That's what I put for A. It's kind of a silly question, is the truth up front. But that's it. Good. If there's no more liquid ethanol turning into gas, then we've reached that equilibrium at that point, and so we are at 100 torr. Is the liquid still turning into vapor? Sure, at the same rate the vapor is turning back into liquid, and so we get the same overall pressure. It then says B, the flask is heated. We answered a question like this not too long ago. The flask is heated to 45 degrees Celsius and the pressure in the flask increases. Good. In terms of kinetic molecular theory, provide 2 reasons that the pressure in the flask is greater at a higher temperature. There's 3 different reasons. The 2 I would go with, if you increase temperature, increasing temperature increases particle speed, heat them up, speed them up, and the particles will hit the walls of the container more often. Increasing pressure. That's the first one for me. The second one, increasing that kinetic energy, increasing temp increases kinetic energy, so the particles hit the walls of the container with more force, increases pressure. Those are the 2 I would go with. What else is happening as we increase the temperature? I think it says the pressure increases. What else could cause the pressure to increase? If you're increasing temperature, then you're probably causing more of that ethanol to turn into vapor, so you have more vapor particles. This is the third one you could use, and more molecules of gas mean more pressure as well. So you could put that there's more moles of ethanol in a vapor state, which increases the pressure. That'd be fine too. Then we say, in the second experiment, a much higher temperature, sample of ethanol gas and a copper catalyst are placed in a flask. Temperature is held constant. We have initial concentration, and then there's a decomposition reaction that starts to take place. And they give us the decomposition reaction right here. And they give us 3 pictures, and we love those pictures. Those pictures should start to look really familiar to us, so we like those pictures that they show us because we know we're dealing with rates now, and they give us concentrations over times, and we have this decomposition reaction coming forth, and then it starts to ask us some questions about this. Let's talk really quick. Be careful the order of the pictures. This is just concentration versus time. That's 0 order. This is reciprocal of concentration versus time. What is that one? Because they didn't put them 0 first, second. They put them 0, second, and then natural log of concentration versus time. They put first over here. It's not a big deal in this one because 0 orders our answer, because that's our linear line. But man, don't get caught when they put reciprocal. If this is linear, man, make sure you pay attention to the axes there. Don't get caught. So C says determine the order of the reaction with respect to ethanol. Justify your answer. Reaction is 0 order because the graph of concentration versus time is linear. That is only a justification if you have a graph present. If they just give you a set of data, you either have to graph it or you're going to have to graph it to use that as your justification. But if they give us the graphs, that is our justification. Concentration versus time is linear, so that means it's 0 order. That's it on C1. Then C part 2 says write the rate expression, or write the rate law for the reaction in part 2. So here we go. If it's a 0 order reaction, there's only one reactant here. All integrated rate laws, you're only dealing with one reactant at a time anyway. Doesn't mean the equation has one reactant, but there's only one reactant here in part C2. Because this is 0 order, rate would equal baby K times the concentration of that reactant to the 0. What's the concentration of that reactant to the 0 power? And that's 1, and so rate equals K. That's our whole rate expression. Just like that. Then we got part 3 that says determine the rate constant for the reaction including units. So now we need to solve for K using the rate. So a couple different ways we could look at this. What is rate? Rate is the change in concentration over time. That's it. Change in concentration over change in time. So we can simply use whatever points we want and find a change in concentration over time, and it'll work out just fine for us. That's how the College Board did it on theirs. And so I'm going to do it that way really quick for us, and then I'll show you how this comes about. So change in concentration, it's always final minus initial. And so for me, I'm gonna choose a nice point that hits an axis point so I know. So here we've got final concentration, 0.006. That's the point I'm gonna use. Minus the initial concentration, I had 0.0100, all divided by the change in time. That's final time, 1,000 minus 0. We got 1,000 here for our time. Because this is a negatively sloped graph, rates can't be negative, so there's going to be a negative sign that gets stuck out in front of this thing. And we end up, when we plug all this in, the rate is going to equal 4.0 times 10 to the negative 6th. Rate is in molarities per second. Because our rate equals K, because our rate equals K here, that is our K value. And I would come back and write K equals, so we define it, 4.0 times 10 to the negative 6th. That's molarity per second for our K value. Good? Where does that come from? It comes all back from this. Look at, if we're 0, this is, we like to linearize this stuff, right? And so the concentration final would equal negative KT plus the concentration of the initial. That's a 0 order reactant. All we did was plug in our final concentration, the 0.006, our initial concentration, the 0.01, and then our time was 1,000. And we plugged that in and we solved for K. Works just like this. If this was a first order reaction, we could come back and do this. Natural log of final equals negative KT plus natural log of initial concentration. If it was a first order reaction, that's how we would solve for the K. And if it's second order, it would be 1 over final would be equal to, be careful, this one is a positive, so it's KT, no negative sign, plus that plus the reciprocal of the initial concentration. So this is where we fall back to, right? When we're looking at something and we have initials and finals, fall back to that. So anyway, that's part 3 on C. And then we've got one little part left, part D. Says, the pressure in the flask at the beginning of the experiment is 0.4 atmospheres. If the ethanol completely decomposes, what would the final pressure in the flask be? If the ethanol completely goes to products in this reaction, well, if we started with 0.4 atmospheres of that, and all of it goes away, we would end up with 0 pressure there. We started with 0 of these. How much would be gained if I lost all of that here? How much would be gained here? 0.4 atmospheres. It's a gas. And how much would be gained here? 0.4 atmospheres. So what would our total pressure there be at the end of that thing? Our total pressure would be 0.8 atmospheres. So D, the pressure, what's the final pressure in the flask? 0.8 atmospheres. Because there are 2 moles of products for every, and I would probably put gaseous products, you can slide that in there, 2 moles of gaseous products for every 1 mole of ethanol reactant. And so our pressure there is doubled. Pressure is proportional to the number of moles. Hopefully that makes sense. We will see you soon.